Hello students. So we are moving our concept of optimization of column performance. So on the previous lectures we have seen that how we have actually improved our column performance. Particularly with regard to resolution, we have seen that what are the different factors which were taken into account. For example, we have discussed performance in terms of retention factors, we have discussed it in terms of selectivity factors, we have discussed in terms of the number of theoretical plates. So we are moving this concept forward in the next coming slides. So let us start our journey. So flow rate, how it is going to affect the resolution. So you can see a pictorial representation. Now if you can see that as soon as you increase the flow rate, then there is an exponential increase in the resolution. You can see that. And there is a certain point. This is a certain point before which, on increasing the flow rate, the resolution increases. But after that point, for example, if you drop a perpendicular like this, then after that point, what is happening, that your resolution is decreasing. So there is actually an optimum point at which you have to have the best resolution, and that optimum point is actually determines what is called as the optimum flow. That is the optimum flow. So you have to have a balance between the speed of your mobile phase flow, and which actually relates to the diffusion. So what you have to do, you have to, if you want to increase the resolution, then you have to have optimum speed. But one thing which you should note at this point is that if you are going to increase your mobile phase velocity very much, then what happens, that RS is going to decrease, because now the CU term becomes dominant. This CU term is our, our the old term which we get from that, that is H equal to A plus B upon U plus CU. That is our Van der Meter equation. So if you increase it too much, if you increase the velocity too much, then it will actually increase CU term, and the CU term will increase in the HETP, that is the height equivalent to theoretical plate. And if the height equivalent to theoretical plate will increase, then definitely your efficiency, your column efficiency is going to compromise or is going to decrease, because it is N is equal to L upon H. So the moment you increase H, the this efficiency will be compromised. So you have to have an optimum velocity of your mobile phase, not very low, because if you have low velocity, then this term will come into picture, then this term will become dominant, that is your diffusion will be greater, which we found in case of GC, which we have discussed previously. So you have to have an optimum velocity, that is CU must be kept minimum. Okay, so moving forward with this, let us see what are the implications of this Van der Meter equation or the velocity in terms of some practical situation. Let us suppose a pharmaceutical analysis. Here we have a drug which contains certain impurity. So initially, when we resolve it, when we run the chromatogram, then we can see that it has an overlap like this. It is overlapping peak, that is the impurity peak is coming along with your drug. This is the drug peak, for example. Drug peak. So it is actually merging with it. So what we have to do, we have to separate these two peaks. That is, we have to have RS greater than or equal to 1.5 for an ideal resolution. We have to keep this in mind, that ideal resolution will only be achieved when RS is 1.5 or greater than that. So that can be adjusted by, for example, that can be simply adjusted by adjusting the pH, because if you adjust the pH, then the selectivity factor will increase, and among all the factors, selectivity factor is the most dominant one, because a little increase in it can cause a great change in the resolution. Okay, so what you have to do, you have to always look for changing of your alpha rather than anything. Okay, we have already dwelled on it. So what you have to do, initially if you get an overlapping peak, then you have to adjust. Sometimes you can adjust the pH, then increase in adjusting pH can lead to increase in the alpha, and that actually increases the RS value. Here it is 1.8. That 1.8 is actually an ideal resolution. That is, it is ideal peaks are obtained. Ideal peaks or ideal peak is obtained. So what you have to do, you have to always look for resolution, and the Food and Drug Administration actually now makes it mandatory to have an RS value of 1.5 to have a good purity check. Okay, that is this. So now let us see another example. Let us see in terms of environmental sample. So we can actually ascertain the presence of pesticide by simply running the chronogram of the sample. Now another important point which we have to discuss here is the mobile phase adjustment, that how actually mobile phase comes into picture. Let us, for example, here we have given you an acetonitrile water ratio. Let us see a common issue. Let us suppose we have a mixture of, instead of acetonitrile, let us take a mixture of methanol and water. Let us see a practical situation where we have a mixture of methanol and water. Let me draw a chronogram and then we are going to discuss it. Let us draw a chronogram. Initially, we will be having this is a little bit going, a little more. Now if we have a chronogram and here it is the resolution time, for example, this is the resolution time, and here it is the, of course, the detector response, here. Now let us suppose there are actually four cases are given here. Let me mark it from the baseline. We are starting from 0, then we have 20, then we have 40, then we have 60, and then we have 80, and finally we have 100. Now there are three cases actually. This is, let me say that this is case number 1, case A. This is, for example, this is case B. Okay, and this is case C, and this is the final one, case D. Now here we have a chronogram, and the only difference here, in case A we have 70% methanol and 30% water. In case B we have 60% methanol and 40% water. Similarly, we have here 50% methanol and 50% water. Here we have 40% methanol and 60% water. Now we all together we get, for example, here it is a clear case. We get component 1, component 2, component 3, component 4, and component 5. So what we are actually seeing here, it's a practical situation of mobile phase adjustment, where our mobile phase is composed of two solvent, one is methanol and the other is water. And here we have a chronogram which is depicting the detector response versus the resolution time, that is the TR. Now students, tell me which is one is the best one, which is the best resolved. Okay, I suppose most of you might be saying that, sir, this is the D case is the best. Yes, D case is the best. It is resolving all the peaks. That is, here if we going to say 1, 2, 3, 4, 5, all the 5 components are resolving. And this is actually, these components are the derivatives of actually 9,10 anthraquinone. For example, number 1 is 9,10 anthraquinone. Number 2 component is you can say dimethyl anthraquinone, 2-dimethyl anthraquinone. Third one is 2-ethyl 9,10 anthraquinone. Similarly, the fourth one is the butyl substituent. So these are all derivatives of anthraquinone. But you can see that out of these 4, in case A, there is no resolution. So we cannot say this is good case. Okay. Similarly, case B, here the resolution is not good, but still you can see all the 5 peaks. 1, 2, 3, 4, 5. Okay. So again, the resolution is poor. So we cannot accept this chronogram also. In the case D, you can see that the resolution is very good. You can see all the peaks, well separated peaks. But again, there's a hidden fact. There's a underlying issue that although the resolution is good, but you can see that it is taking too much time. It is taking around 38 minutes. So if you combine this resolution with time, then you can say that the separation is taking too much time. But on the contrary, you can see that this case C, actually, where we have a 50-50% mixture of methanol and water, all the peaks are resolved. All the peaks are resolved, not as good as D case, but still all the peaks are resolved, can be seen 1, 2, 3, 4, 5, that are the derivatives on 9,10-inthraquinone. All the peaks are resolved, and again it is taking not too much time. If you see the time, then it is not too much. Okay, it is around 20 minutes. On the contrary, it is around 40 minutes or so. So it is taking too much time. So what the best case, the best resolved case is the case C. Similarly, on changing the alpha, you can adjust the RS value, that is the resolution. For example, when you move from 1.0 to 1.1, the resolution increases to 50%. So this is how you have to look different aspects of resolution, of optimization of your column. That is, you have to actually bring out the best performance from your column in terms of resolution. Okay, in terms of resolution means separation of peaks with sharp, or you can say with as minimum of width as possible. Okay, so peaks must be narrow and they must be well separated. That is actually the resolution. Okay, so and this resolution must be brought about in the minimum amount of time. That is actually the optimization, full optimization. That is resolution along with time. Okay, so this is how practically situations occur. Now let us move forward and see that in biochemical mixtures, for example, that is the separation of amino acids by X-ray chromatography. We are going to see it when we discuss the HPLC. Again, the temperature actually controls N, the efficiency. And we see that how actually the increasing of temperature leads to change in viscosity, and the viscosity becomes dominant actually. Similarly, slight shifts in peak, that is called as pH tweak, that is the change in the concentration of the hydronium ions or the hydroxyl ions. A slight concentration change can affect or can shift the value of alpha. Okay, so what our basic aspect of optimization is that we have to improve our resolution. Okay, and in any case it must be greater than or equal to 1.5. so we have to take a special care about the resolution, and along with minimum amount of elution time. So these two factors have to be accounted. Now, gradient elution. This is actually a very interesting fact, very interesting parameter. Gradient elution. Generally, what happens, we have two type of elution. Number one is the gradient elution, and number two is the isocratic elution. Isocratic is written here. So we have actually, that is gradient elution, and we have isocratic. Now, as the name suggests, isocratic elution is that elution in which we are using the same concentration of mobile phase throughout. There is no gradient with regard to change in polarity, with regard to change in size, with regard to change in any other property. While in gradient chromatography or in gradient elution, we changes the certain properties to have a better or optimized elution of different components through a column. For example, in gradient chromatography, what we do, we sometime in most of the cases, what we do, we actually changes the polarity of our solvent. For example, we changes from non-polar to polar, and because of this change, we can actually separate complex mixtures using the gradient illusion. While in case of isocratic illusion, we can only separate similar or almost similar components of a mixture, of a simple mixture. But in case of illusion, when in case of gradient chromatography or gradient illusion, we can actually separate complex mixtures or complex components which have entirely different properties, because now actually we are using the tool of polarity. And again, when we change the polarity, then we get actually array of components on the basis of their polarity. For example, if we are going to start from non-polar to polar, we can have an array of compounds or components if present on the basis of their polarity. Okay, so this is actually called as the gradient illusion, or the illusion give rise to gradient chromatography or gradient chromatogram. So what we have to have, we have to change the composition change during run, so that we can get dynamic retention factors and dynamic separations. Okay, similarly, this gradient chromatography actually leads to reduction in time, and again we get an ideal peaks also, that is the sharp peaks. Otherwise, in isochromic chromatography, the retention time is too much, and again the resolution is not very good. So for separating complex mixtures, what we do, we generally carry out the gradient chromatography, where we can actually change polarity, and on the basis of change of polarity, we can elute a number of complex components of a given mixture. Okay, so what are the optimization? There are, we have learned a lot about the optimization, and all the factors which we have learned with regard to optimization, maybe it resolution, maybe it narrowing of peaks, maybe it separation of peaks, all the properties, all the aspects were practical in nature. Now it's time to cut short our time to have some dry runs. Okay, so to have some dry lab studies, to have some in silico studies to ascertain the column performance theoretically, even before going practically to the lab. So there are certain aspects. Number one is the design of experiment. We carry out certain experiments theoretically, just to make sure what type of, or what may be the length of the column to have a better or ideal separation, what must be the height of the theoretical plate to have an effective separation, how much the distance should be there between the two peaks to have a better resolution. So all this can be done by doing certain experiments on computer, or you can say theoretically. And for example, there is box Benken approach, which gives you an idea that what will be the response curve by taking certain aspects into play. Similarly, we have surface methodology studies, which tells you about the possible number of theoretical plates which your column should have to effectively resolve your different components. So these in silico studies gives you some predicted RS values, and on the prediction you can then run practical experiments. You can then carry out practical separations. Okay, similarly, there are certain softwares available to help you out, and the common softwares are the dry lab, the chrome sword, and the design experiment, which actually helps you to visualize your column performance on theoretical basis using certain computer programs. So to minimize your time, to minimize your efforts, to minimize the chemicals, so that everything will be, you can say, you can restrict everything before practically moving to the lab to perform optimization or to perform chromatographic separation. So what is the important message of this particular slide is that RS contour plots help you to visualize the optimal zone. What this actually means, that by actually plotting RS values, you can actually plot RS values in 2D actually to get the contour plots even before going to lab. So you can check your RS value of different components by selecting different mobile phases, by changing the polarity of the mobile phases, by just running few computer programs. Okay, so this is actually, these statistical tools help you to minimize your time of separation, to minimize, to doing certain, to to undergoing a number of experiments. You can have a few one on the basis of the selection done by your computer on the basis of these programs. So column length, actually one of the important things you have to visualize in terms of column length optimization. We know that the number of theoretical plates are directly proportional to the length of the filled column. We also know that longer the column, better will be the resolution. But at the same time, we have to account for the additional time it is going to take if we are going to make our column a little bit long. So, and we have to check the optimum RS value, that is 1.5. So, let us take an example to understand the importance of the optimization with regard to the length of the column and with regard to the TR and TS values. So let us suppose we have a two component mixture A and B. Suppose we have a two component mixture and TRA is coming out to be, for example, it is coming out to be 12 minutes. Similarly, TRB is coming out to be 14 minutes. You can take WA as 3.4. Width of the second peak may be called as WB. Let it be 3.6 centimeter. It is 3.4. Now, you can calculate the resolution. Now, let us calculate the resolution RS. RS, we know that it is twice of TRB minus TRA upon W of A, width of peak A plus width of peak B. Now TRB is that component which is eluting at a later rate, that component which is having a stronger interaction with your stationary phase. So let us calculate. It is twice of 14 minus 12 upon 3.4 plus 3.6 and is coming out to be 4 upon 7, that is 0.57. Okay, so your resolution comes out to be 0.57. This is very poor resolution. In fact, resolution of 0.57 implies that your peaks are actually not resolved. They are not resolved. So now there is a need to optimize your column. Let us suppose the data given to you for this, let us suppose L is 30 centimeter. So now it's time to do optimization with regard to R, with regard to, you can say L, and with regard to H. Okay, so let us see that how we are going to resolve our, or how we are going to optimize our resolution, our length of column, filled column, and the height equivalent to theoretical plate. So let us calculate the number of theoretical plate first. So number of theoretical plates can be calculated by L upon H. Okay, that can be calculated by L upon H. Now L is 30 centimeter and H we have to calculate. Okay, so we have the formula N is equal to L upon H. Now let us calculate the number of theoretical plate first, and then we are going to calculate the height equivalent to theoretical plate. So for calculating the number of theoretical plate, we have the formula 16 TR upon W square. So by doing so, we have a two component system here. Okay, component A and component B. So we have to calculate two different theoretical plates. So let us suppose it may be NA, then NA is equal to 16 upon TR, TR of A. TR of A is 12 minute upon W is 3.4 whole square. And it comes out to be 199 plates. Okay, and it comes out to be 199 plate. On the similar basis, we are going to calculate NB, that is the number of theoretical plates for constituent B. NB again 16 into TR of B upon W of B. Okay, that was the general formula here. That was the general formula, and we have actually substituted our component B here. So NB is equal to 16, TRB is actually here, it is written 14 minute upon WB is 3.6 centimeter whole square. Okay, so NB comes out to be 241 plates. Now average plates you have to calculate. N average is equal to NA plus NB upon 2, that is 199 plus 241 upon 2, that comes out to be 220 plates. Okay, that comes out to be 220 plate. Now you can calculate the length of the, first of all you have to calculate H. H is equal to L upon N. L is your again 30 centimeter here given to you, 30 centimeter. So 30 upon 220. So that comes out to be 30 out of 220. That comes out to be, H comes out to be 0.13 centimeter. So this is how you have calculated the number of theoretical plates for each component, and then you have taken the average, and on that basis you have calculated the height equivalent to theoretical plate. So you have to, now you have to run a column with regard, now you have to ascertain what type of length actually needed. So there's a formula to this, and let us explore that formula. Okay, that formula is resolution of, suppose let me write it P, that is practically resolution is coming, and the resolution which is desired or the ideal one. Okay, ideal one is the 1.5 resolution, and here the resolution which is coming is we have, it is you can say here it is given 0.57. Okay, this is one. So that actually is equal to you can say under root of n of the practically occurring upon under root of n, that is the desired or ideal. That is the formula. So in this formula you have to put your values actually. Now if you put your values, then RS comes out to be 0.57 upon ideal one is 1.5. That is the resolution where your both the peaks are resolved, is equal to under root of n. Number of theoretical plates comes out to be 220. So under root of 220 upon under root of n, that is the ideal plates which must be there in your column for a better resolution. That is, you are calculating the number of plates in the optimized column, and that Ni, if you calculate, then Ni equal to comes out to be 1524 plates. Ideally it should be coming. Ideally how many plates should have? 1524. Now you can see the difference. That is, ideally you should have, your column should have 1524 theoretical plates, and how many they are actually have? Only 220 plates. So, and because of the less number of plates, your column is not optimized. It is showing a resolution of only 0.57, which is actually 1/3 of the ideal resolution, that is 1.5. Okay, now what we have to do, we have to optimize the length of the column, and for optimization of this we have the formula n is equal to L upon H. Okay, now your ideal plates which must be coming is how many plates? 1524. You have to calculate the length of the column, that is the optimized column OP, upon the height which you have calculated, H was 0.13. Now L, the length of optimized column, if you are going to solve it, it comes out to be 198 centimeter. Now you can see a big difference that practically your column is only 30 centimeter. But to have the best resolution, its length should be 198 centimeter. Okay, this is the beauty of calculation, that even without performing any laboratory experiment, without even using any of the solute, or without taking your different components of the mixture into column, you actually optimize it by simple calculations. Okay, so your length must be 198. Now you have optimized the length. Now it's time to optimize the retention time, because your resolution of 0.57 is giving you this type of problem. So you have to resolve in terms of this TRB. That is, you have to resolve the time, the difference in the time of elution of the two peaks, that is the component A peak eluting and at component 2 peak. So it is actually, it's a difference of only 2 minutes. So now practically we are calculating that what must be the ideal difference between the two peaks, so that the resolution of 1.5 can be achieved. So let us again do some calculations. So now the calculation is TR of component B, okay, upon TR of component B, which must be required, that is actually you are practically getting it, is equal to, RS of the value which you are getting practically upon RS which is required. It is the square of both. Now TRB, practically you are getting your TRB is 14 minute. Don't write minute here, because we are dealing with dimensional quantities. 14 upon TRB, okay, which is required, is equal to RS, that is coming out to be 0.57 square upon the ideal, which is 1.5 square. Okay, now if you solve it, then you will get TRB required. If you solve it, it will be coming out to be 96. It is coming out to be 96 minutes. So you can see the difference. And this is how actually you optimized the different parameters. You optimize your column length, you optimize your resolution, and you optimize the value of retention time. Okay, so longer the column, of course better the resolution, but you have to account the time. Similarly, optimum resolution cannot be achieved on the basis of the time. Okay, although you get a resolution of 1.5, but it took around 1 or 2 days, then that does not carry any sense. Okay, so let us move forward and let us see the effect of temperature. It's a very important effect. The moment you increase the temperature of any system, the viscosity decreases, and the moment viscosity decreases, it increases the efficiency of your column. But there is actually a issue that sometimes your selectivity factor changes unpredictably, and you cannot predict it. That is the most important issue. You cannot predict it. In certain cases, for example, it can be seen that by simply increasing a temperature from 25 to 40 degree, for example, the resolution is increased to around 40%. That is from 1.2 to it increased to 1.6. But each time since you cannot predict the alpha, so each time you are going to increase the temperature, you have to keep a very close eye with regard to the selectivity factor. Okay, so what are the advantages of optimization? Why we are so concerned with optimization? Number one, that the optimized column always have improved resolution. That is always a resolution of greater than or at least equal to 1.5. And once your resolution is improved, you can accurately quantify the different components present in the mixture. And if your system or if your column is optimized, then of course you can always look for shorter times. An optimized column gives you better reproducibility. That if, for example, if you are going to run 5 experiments, 5 runs or 10 runs, each time you are getting the same TR1 value, TR2 values, same time, same values of alpha, same values of retention factors, every time you are getting same values. And if your resolution is good, if your peak separation is better, you have a sharp peaks, then you can always detect the presence of any impurity. Because the moment impurity is coming, it will give you unresolved peaks. It will give you superimposed peaks. So you have to look for the peaks with regard to optimization, peaks of impurities with regard to optimization of your column. So there are certain limitations also. Again, the columns are very costly. You cannot actually compromise those expensive columns with some untrained person. So only a trained person can handle it because the columns are very expensive. There are certain back pressure also. Back pressure means that is the pressure felt by your mobile phase while moving through the column. There is always a back pressure. So you have to have minimize the back pressure in case where the number of theoretical plates are more. So there are always chances of some back pressure as you keep on increasing your number of plates. So you have to account for the back pressure also. Similarly, although alpha is very important, that is selectivity factor is very important with regard to resolution, but its range is limited. You cannot vary too much. That is, the range of alpha is limited. Again, most of the time you have seen that we actually dealt with A and B components. So this is very good for the resolution of one component or two component or sometimes maybe 3 component, but it becomes complex situation if your solutes, if your components are greater than 2. And there is always a trade-off between the resolution and time. You have to look that the resolution, we have already discussed it, that sometimes you get a very good resolution but at the expense of time. So time is money actually. So you have to have always looked that whether your good resolution is taking too much time, it is claiming too much time. If it is so, then you have to restrict that time also. You have to have shorter runs with as good resolution as possible for an optimized column. Okay. So some of the hidden insights. One is that in case of mixed stationary phase, you always have certain interactions. Okay. That is, sometimes you have hydrophobic and ion exchange interactions, and that actually gives you a greater alpha, that is a greater separation. So pre-column derivatization. If you derivatize your column, if you derivatize your stationary phase, then you can actually what you can do, then you can tailor your interaction of the solute molecule with the stationary phase. So you can tailor that retention time of the solute molecules with your stationary phase on the basis of the derivatization, on the basis of functional group interaction, on the basis of just changing certain functional group. For example, if your solute is amine rich, then what you can do, you can just add certain carboxyl group, then you have a better interaction with it. Similarly, in case of microchip HPLC, you can have very small, the size of height equivalent to theoretical plates is very small in case of microchip HPLC, and that small h will give you ultra fast analysis as well as extremely good resolution. So what you have to do in 2D liquid chromatography, you can have a multi-dimensional optimization. You can optimize your column in a number of ways. So in summary, what we have covered up to this point with regard to optimization is that resolution is very important, and resolution practically depends on 3 factors, that is the efficiency of column, selectivity factor, and the retention factor. So resolution is the most important key for the performance, for deciding the performance of your column. while separating a 2-component or a 3-component mixture. And this resolution depends on number of theoretical plates, alpha, that is selectivity factor, and k dash, that is the retention factor. We have discussed all these three factors in detail in our previous slides. So again, we have also discussed that first of all, initially you have to optimize alpha, because alpha has the greatest effect on resolution. A simple change of a factor of 0.4 actually doubles your resolution, while the other factors, that is n or k dash, are not so dominant with regard to the resolution. So you always have to fine tune your alpha first while optimizing your column performance. And we have also seen some real life examples with regard to pharmaceutical, with regard to environmental detection of toxic gases, and also we have seen that how RS is very important, because now the FDA has already said that RS of 1.5 is mandatory. So in the end, the takeaway message is that chromatography is a beautiful branch of science that deals with color, and it is actually making your chaotic mixture into a well separated components, where each tributary is giving you a pure component. That is what actually chromatography has done. Chromatography has streamlined the whole ocean into tributaries of each component having definite properties. That is, this chromatography has made the separation super easy. So with this, I am open to questions, and I would like to have a very good question answer session with you all in our interaction session. Thank you.